Hello, my name is Aarya Mishra and my USN is 007. I'm here today to talk about pipelining in computer organization or computer architecture. Pipelining is the process of arranging the hardware so that simultaneous execution of multiple instructions takes place. Now, what that means is that we can arrange two or more processes to run concurrently so that it takes up less time. What that means, in simple terms, let's imagine a restaurant. Now, this restaurant is going to have a kitchen. And let's imagine this kitchen only has three cooks. One of them can only cook the appetizer, one can only cook the main dish, and one can only cook desserts. Now, if the cook who's cooking the main dish keeps waiting for the cook who's making the appetizer to finish before he starts, it's going to take ages for this meal to get done. And if one meal doesn't get done, the second meal is never going to get done. And so no one is going to come to this restaurant because it takes so long for them to make food. Similarly, each computer has several processes, and each of these processes are required to run a program. If one process waits till the other process is done executing to start its execution, it's going to take forever for us to run a program. And no one wants a system that takes hours together to run. The whole point of computers is to make our lives easier. Let's visualize this with an example. Here, let's consider two processes, P1 and P2, and we'll see them at four stages of execution: S1, S2, S3, and S4. We see here that P1 has to complete execution, which it completes at 4 seconds, before P2 can start execution. This is a system where we do not use pipelining. See how it takes us 8 seconds to complete both of these processes? Now let's compare this to here. P1 and P2 start execution almost at the same time. P1 starts a second earlier, but you see then that they run concurrently. Now, what benefit this provides us is visible here at the top. A system that uses pipelining is able to complete both of these processes in 5 seconds, whereas a system without pipelining uses 8 seconds to do the exact same thing. Now, if 5 seconds and 8 seconds is not that big of a difference, why do we care? It's because to do something very simple like addition, there are multiple processes that need to be taken into account. Getting the data, executing the data, and if all of these processes keep waiting for each other, any simple process is going to take way more time. These 3 seconds are going to add up to minutes, and those minutes are going to add up to hours. Like I said, no one wants a system that works really, really slowly. How are we going to divide this process? Surely we can't just divide it randomly. Here we come to the stages of instruction execution. There are 4 main stages: fetching, decoding, executing, and write back. In fetching, we retrieve an instruction from the memory. A computer, despite what we think, is not very smart. It needs instructions to tell it what to do. Then these instructions need to be decoded. After fetching the instruction, the computer still does not understand what needs to be done. It needs to then sit and decode so that we can understand what data needs to be collected and taken from which register. This brings us to the execution part, which is the bulk of any process. Arithmetic operations, logical operations, all of these take place in this block. And then storing the result, obviously. Completing an operation doesn't mean anything if we don't have a result to show at the end of it. So let's discuss the types of pipelining. There are 2 main types of pipelining: arithmetic pipelining and instruction pipelining. Arithmetic pipelining is focused mostly on the ALU, the arithmetic logical unit. What it does is that it breaks down arithmetic operations into smaller steps. Like I said earlier, fetches operands from the register, it performs the arithmetic operation, and it stores this result back in a register. Now, while all of this happens, a processor sits idle for very long. When you are fetching operands from the processor, what we can do is that we can start the next instruction a little bit earlier. This avoids the processor from sitting idle for so long waiting for this data to reach the register. And when a processor sits idle, it's inefficient. The main thing we want to do is maximize efficiency. Coming to instruction pipelining, The cycle that I mentioned earlier, the fetch, execute, decode cycle, what we do here is that we break down each instruction into these specific stages. If process 1 is executing, we say process 1 is now fetching the instruction, it is decoding the instruction, it is executing the instruction, and then it is writing it back. Once process 1 fetches the instructions and it begins decoding, what we do is that we begin the fetch of process 2 as well. Now, since both of these processes are running, we save some time that it would have taken for process 2, where it would have waited for process 1 to reach the write back part. But why are we going through all this effort in the first place? Why are we dividing an instruction into 4 parts? What is the need of pipelining? Now, the two main things are increased throughput and improved performance, which are very technical terms, so let me explain them for you. Increased throughput means that a lot more instructions can be completed in a shorter amount of time. Like I said, in 5 seconds, we can finish the first process as well as the second process. Whereas without pipelining, we could have only completed one process. That is the throughput, amount of instructions completed versus the time taken. Improved performance means that the overall execution time is reduced. Like we discussed earlier, from 8 seconds, we can bring it down to 5 seconds. So pipelining is perfect, right? It is the be-all end-all to all of our problems. Well, not exactly. There are several problems that occur while we consider the concept of pipelining, and we call these pipelining hazards. There are 3 main hazards that we're going to look at today: data hazard, control hazard, and structural hazard. We'll go into depth of each of these, but in one line, a data hazard is when an instruction needs data from a previous instruction that hasn't been completed yet. A control hazard is when the execution of an instruction changes the flow of control, disrupting the pipeline. What this means, we'll see later on. And a structural hazard is when 2 instructions attempt to access the same memory location simultaneously. Let's take a closer look at data hazards. Here we have several operations to the left side here: addition, subtraction, OR, and an XOR. And this is the time taken for each of these operations to function. If we zoom in on this addition process, we see that this process ends with the creation of x3. That is, the value that is read is stored in the register x3. Subtraction needs x3 before it starts existing. Do you see how pipelining messes up here? x3 doesn't exist yet, but all of these processes, except XOR, need x3 before it's even created. In this process, we can't do anything. We have to wait until addition is completed. Pipelining fails here. That's what data hazards are. This instruction needs this data before it's created. Now, data hazards are also of 3 types. The most common one is read after write, when one instruction makes use of data from a previous instruction, like we saw here with the x3. The second one is write. This is also more commonly known as a race condition. The second the second instruction and the first instruction are both competing to get read. And the third one, which is the most rare, is write after write, when simultaneous instructions are used. See here, in add and AND, this occurs simultaneously. This is a write after write instruction. Moving forward, control hazards. Control hazards are not quite easy to explain, so we're going to have to use this table again. What a control hazard does is that it skips the statement of execution, and it renders pipelining, well, useless technically. Do you see this JMP statement? This is a jump statement that we've mentioned here. And what this does is that it skips over this instruction and it jumps to register 640. Now this pipelining, everything that we had designed, everything that we had decided was going to happen, doesn't happen because the jump instruction moved it over. Same with a branch over here. A branch instruction will start a different chain of execution. It will branch out. This disrupts the pipeline, or it causes the pipeline to wait for a longer period of time, which is also called a stall. Control hazards need to be fixed. So what are the solutions of control hazards? So the control hazard solutions that we have are of 4 types: stall prediction, dynamic branch prediction, and reordering instructions. Stall and prediction are both very easy to understand, so I won't go into depth with the two of those, but dynamic branch prediction and reordering instructions need a little bit of explanation. In dynamic branch prediction, we use a branch table buffer. What we do here is that we keep a record of all the instructions that we've evaluated. Consider it to be like a cache memory. Now this keeps a record of when a branch started, the PC address it started at, and the PC address it went to. So once the branch is complete, it's easy for us to go back to the original instruction. The branch table helps us understand where exactly we branched off so we can get back to our pipeline. Whereas in reordering instruction, we ignore this completely. We restructure the pipeline so that we never have a statement where there's a potential to get lost. The last hazard we're going to look at today is a structural hazard. So when two or more instructions in the pipeline require the same resource at the same time or the same clock cycle, a structural hazard occurs. What happens here is, say process 1 and process 2 both require the same register or the same memory location, or they even need to perform the same arithmetic operation. The hardware can't support both of these processes functioning at the same time. So what we do here is that instead of making these processes run parallelly, as we've been doing, we have to make them run in a series. Does this take yet less time? No. It takes a lot longer for us to wait for process 1 to finish before process 2 can run. But it's the only thing that the hardware supports, so we have to do it anyways. That's the last of the hazards. And so let's have a quick little recap. Pipelining is the process in which we make two or more processes run concurrently in order to increase the efficiency of the processor and reduce the throughput. How we achieve this is by dividing an instruction into four parts: fetch, decode, execute, and write back. There are two main types of pipeline: arithmetic pipelining and instruction pipelining. And pipelining has three main types of hazards: a data hazard, a control hazard, and a structural hazard. That concludes our topic. Thank you so much for listening.